Hi everyone. Um, in this video, we're going to look at end behavior of algebraic models. Okay, so definitely, if you recall, we did work with problems that deal with end behavior, right? What is the end behavior of rational expressions, correct? Rational functions. You'll see that this is very similar, except now we have it in context, right? It is in context. It's a real life situation. And let's take a look. All right. So first problem says Elena knows that Leah has a garden with an area of 100 square meters. She does not know the specific width W and the length L of the garden. The graph below represents the widths that correspond to the possible lengths of Leah's garden. Okay, so in this particular function, what's given is a graph of possible values for length. So the length is on the y-axis and the widths are on the x-axis, okay? But regardless of what the lengths and the widths are, the function has to give you the area of 100 square feet. Okay, so anywhere that you are on the function, if you take the length and the width at that particular point, the product of the length and the width must be 100. Okay, so let's take a look. As the possible widths of Leah's garden increases, what does the possible length do? So as the possible widths of Leah's garden increases, what does the possible lengths approach? Well, as the widths increase on this function, correct? As you go from left to right on this function, what's happening to the values of y, or f of x, in this case, length? As you increase the width, the length, as you can see, is dramatically decreasing, correct? And then it levels off, but as you can still see, the lengths are still decreasing, correct? And how far? So what value is the length approaching as W increases without bound? Okay, and it's pretty obvious that what we're asking is, as x increases, what does f of x approach? As x goes to infinity, what does f of x approach? Well, f of x here, it keeps decreasing, right, dramatically in the first part, but it's still decreasing, and it's going to keep decreasing until it's approaching what? Until it's approaching 0, correct? And that's why they call this an end behavior problem for algebraic models. Okay, let's take a look at the next one. Raphael purchased his car for $12,000. The value of Raphael's car depreciates over time, decreasing by 10% every year. Okay, so Raphael's car's value is depreciating, right? So it's losing value, depreciating over time. By how much? 10% every year. So Raphael's losing 10% every year on his car. Which of the following graphs could model this relationship? If t is elapsed in time and v is the value of Raphael's car at $1,000. Well, here we can clearly see that he's losing a percentage of his car every year. Okay. However, if you look at the numbers, when we start with what? 12,000, right? So let's start with 12,000. Let's clear the board. Okay. So we start with $12,000. Sorry. Okay, we start with $12,000. This is year 0, right? Year 0. What about year 1? Well, in year 1, he has lost 10%. So 10% of 12,000 is going to be what? 1,200, correct? So he just lost $1,200 on his car. So if you do the math here, it looks like now he's left with what? 1, 0, to 8. So now his car is only worth that much. He's lost $1,200 on the value of his car. So this is how much it's worth. Initially, that's how much it's worth after year 1. Year 2, well, he's going to lose another 10%. So now he's going to lose 10% of what's here. So let's figure it out. He starts with that minus 10% of that. Well, 10% of that is 1,080, right? 1,080. Correct? So now he's down to, what is it? Oops, what just happened? I just lost it. So let me get it back. We are now down. I just got my screen back. So 10,800 minus 1080 is equal to $9,720. Okay, and this is the value of the car at year 2, and it's going to continue losing value. But if you look at these numbers, let's do one more year. Let's do year 3. So he's going to lose another 10%. So now, from year 2, his car was worth $9,720 minus, now he's going to lose 10% of that. So that's going to be, what is it? It's going to be 972. So if he loses 972, now his car is only worth $8,748. So, and this is going to continue on until he either sells his car or, whatever happens afterwards. If you look though, if you look at the money that he loses every year, do you see that the money that's lost, the money that he loses through depreciation is not constant? Do you see that? It's the percentage is constant, but not the amounts. So every year, his car is worth less and less. Therefore, he's going to lose less and less in depreciation. Correct? So 10% of a smaller number is not going to be as big as 10% of a bigger number. So every year he's going to continue losing money, but less than what he lost the previous year. Therefore, this is not, folks, a linear function. He's not losing a constant value, a constant number. Okay? So if we go back here, it can't be a linear function, right? So let's see what the other choices are that we have. Okay, so every year he's losing a little bit less. Okay, so it looks like A and B are linear functions, so that doesn't make any sense. However, C and D definitely looks like they can make sense. Question is, which one is it? Is it C or is it D? Well, the question lies, I believe, we can pretty much tell the difference here. They look the same until maybe year 10. I think if we calculate the value at year 10, let me see here. The question is, as time goes, will the car eventually go to zero value, $0? Or is the value of the car going to approach a certain dollar value other than 0? Well, here, the difference between C and D, and I inadvertently marked C, is in C, it's saying that the car eventually will go to $0 after a while, after 50 years or so, right? It's going to pretty much effectively be worth 0. Here, it's saying that the value of the car is approaching $2,000. Okay, so the question is, after 50 years, is the car going to be worth around 2,000 or is it going to be worth nothing? All right. Well, Is there a particular reason that the car is going to be worth $2,000? Well, I'm not sure that that's going to be it. Okay. Again, there has to be a reason for the car to be worth $2,000. And in this case, there really isn't. The car will continue to depreciate, as you can see. The car is going to continue to depreciate here. It's not going to approach a value of 2,000. Okay. But again, the amount of depreciation will continue to decrease. Okay. Now let's take the next question. Okay. That we can tell about this particular problem is if we wanted to now model this, right, we could say the final purchase price of the vehicle is going to be equal to the initial price of the vehicle times the rate, okay, whatever the rate, whatever the percentage of car we're going to have left. Now, if we're losing 10%, then what are we going to have left? Well, we're going to have 90%, correct? We're going to have 90% of the car, right, left, and raise it to the t power. So let's see what happens. What's the price of the vehicle after 50 years? Well, it's going to be $12,000 times 0.990 raised to the 50th power. Okay, and let's figure out what this comes out to. So if we do 0.9, let's do it, raise it. We're going to raise that to the 50th power. And we're going to multiply that by 12,000. And that gives us $61.84. So in year 50, this car is going to be worth about $61.85. Okay, given a 10% depreciation rate of depreciation. Okay, in other words, how much is the car going to be worth if 10% depreciates? It's going to be worth 90%, right? Every year, so 50 years, starting with a $12,000 purchase price of the car, value of the car. Okay, that's definitely not $2,000. Okay, let's continue. In this problem, we have a committee. Okay, so So maybe because the video is getting long, so I'm just going to cut it right here. All right, and I'll see you in the next video.